Welcome to this problem-solving session on the coding challenge Escape the Ghosts, number 789. In this problem, we'll figure out how to determine if we can reach a target position on a 2D grid faster than the ghosts. Let's dive in and explore the solution step by step. In this problem, you are tasked with escaping from ghosts on a 2D grid and reaching a specific target position as quickly as you can. You start at the origin, which is the point 0, 0. And your goal is to get to the target position by moving one step at a time, either up, down, left, or right. The ghosts are also positioned on the grid and are trying to stop you from reaching the target. Just like you, they can move one step in any of the 4 cardinal directions per turn. If a ghost reaches the target before you, or if a ghost reaches the same position as you at the same time, you lose the game. However, if you can reach the target before any ghost does, or if no ghost can reach the target at all, you win. The task is to determine whether you can escape the ghosts and reach the target safely. You will return true if you can escape and false otherwise. The input consists of an array of ghost positions and the target's coordinates, while the output is a Boolean value indicating whether or not you can win the game. Let's look at an example to understand this problem better. Say the initial positions of the ghosts are given as 1, 0, 0, 3, and the target position is 0, 1. First, you calculate your Manhattan distance to the target. The Manhattan distance is the sum of the absolute differences between the x-coordinates and the y-coordinates. In this case, starting at the origin, your distance is abs, 0 to 0, plus abs, 0 to 1, equals 1. Now, for each ghost, we calculate their Manhattan distances to the target. For the first ghost at position 1, 0, its distance is abs, 1 to 0, plus abs, 0 to 1, which equals 2. For the second ghost at position 0, 3, we start calculating its distance as well. For the second ghost at 0, 3, its Manhattan distance to the target is abs, 0 to 0, plus abs, 3 to 1, equals 2. Comparing these values, your distance to the target is 1, and both ghosts have a distance of 2. Since your distance is shorter than the distance of both ghosts, you can reach the target before either of them does. Therefore, in this case, the output is true, indicating that you can escape the ghosts. Now let's consider another example. Here, the ghost starts at 1, 0, and the target is at 2, 0. Your Manhattan distance to the target is abs, 0 to 2, plus abs, 0 to 0, equals 2. For the ghost, the distance is abs, 1 to 2, plus abs, 0 to 0, equals 1. Since the ghost's distance is shorter than yours, the ghost can reach the target before you. As a result, the output is false in this scenario. In the third example, the ghost starts at 2, 0, and the target is at 1, 0. Your Manhattan distance to the target is abs, 0 to 1, plus abs, 0 to 0, equals 1. For the ghost, the distance is abs, 2 to 1, plus abs, 0 to 0, equals 1. Here, the ghost has the same Manhattan distance to the target as you. This means that the ghost can reach the target at the same time as you, preventing you from escaping. Therefore, the output is false. These examples illustrate how the problem hinges on comparing your Manhattan distance to the target with the distances of the ghosts. Now let's look at the constraints and edge cases to consider for this problem. The constraints specify that you can have between 1 and 100 ghosts, and each ghost's position is defined by exactly 2 integers within the range of -10,000 to 10,000. Similarly, the target position is defined by 2 integers within the same range, and both you and the ghost start at unique and distinct positions. Several edge cases are worth noting. For instance, if there are no ghosts on the grid, the output is always true because no one can stop you from reaching the target. If the target is at the origin, you are already at the target, so the output is also true. However, if any ghost has a strictly shorter Manhattan distance to the target than you, the output is false because that ghost will reach the target first. Finally, if multiple ghosts and you have the same Manhattan distance to the target, the output is still false because the ghost's presence at the target blocks your escape. These edge cases and constraints guide how we think about solving the problem efficiently. The problem Escape the Ghosts asks us to determine if we can reach a target position on a 2D grid before any of the ghosts catch us. You start at the origin, which is the position 0, 0, and your destination is a specific target point, denoted as x, y. The ghosts begin at their respective starting positions, which are given as a list of coordinates. Now, both you and the ghosts move at the same speed, and the time required to reach any position is calculated using Manhattan distance. For reference, Manhattan distance is simply the sum of the absolute differences of the x and y coordinates. Your task is to determine if you can reach the target before any ghost arrives. The key insight here is that if even one ghost reaches the target at the same time or faster than you lose. This means we can focus on comparing travel times. Instead of simulating movement step by step, we can directly calculate the Manhattan distance for both the player and each ghost to the target, which forms the basis of our solution strategy. Now, let's consider the possible approaches to solving this problem. The first approach is brute force simulation, where we would simulate the movement of both the player and every ghost on the grid, step by step. While this might seem straightforward at first, it's extremely inefficient. The grid size is essentially unbounded, and simulating each step for the player and all ghosts can quickly become computationally expensive. More importantly, this level of detail is unnecessary because the outcome is determined solely by comparing Manhattan distances. Instead, we can use an optimized approach based on distance comparison. Here, we simply calculate the Manhattan distance from the target for the player and for each ghost. If any ghost's distance is less than or equal to the player's distance, the result is false, meaning the player loses. Otherwise, the result is true, and the player wins. This optimized approach is far more efficient, as it eliminates the need for simulation and focuses directly on the critical condition, the distance comparison. With a time complexity of O(n), where n is the number of ghosts, it is scalable and well suited for this problem. The chosen strategy for this problem is the optimized distance comparison approach. This method is particularly effective because it takes advantage of the problem's constraints and focuses solely on the key insight that Manhattan distance determines the outcome. By directly comparing the player's distance to the target with each ghost's distance, we avoid unnecessary complexity and achieve computational efficiency. This approach runs in linear time, O(n), even when the number of ghosts is large, making it both practical and scalable. While brute force simulation might be easier to visualize, it is computationally impractical due to the unbounded grid and the need for step-by-step simulation. In contrast, the optimized distance comparison approach is clean, efficient, and directly aligned with the problem's requirements. The only trade-off is that it requires a clear understanding of Manhattan distance and the relationship between distances and outcomes. Overall, this approach strikes the right balance between simplicity, clarity, and efficiency, allowing us to solve the problem effectively by leveraging the mathematical properties of Manhattan distance. This problem challenges us to determine if we can reach a target position on a 2D grid faster than any ghost. Starting at the origin, you and the ghosts can only move in horizontal or vertical steps, with each step taking 1 unit of time. The shortest path between 2 points on this grid is defined by the Manhattan distance, calculated as the sum of the absolute differences between the x and y coordinates of the points. To escape the ghosts, your Manhattan distance from the origin to the target must be strictly less than that of any ghost to the same target. Ghosts move just as fast as you, so even a single ghost reaching the target as quickly as you would make escape impossible. The first step in solving this involves parsing the input to extract the target coordinates and the list of ghost positions. From there, we calculate the Manhattan distance for the player, which is simply the sum of the absolute values of the target's x and y coordinates. Once we have the player's Manhattan distance to the target, the next step is to calculate the Manhattan distance for each ghost. This is done by taking the absolute differences between the ghost's x and y coordinates and the target's x and y, then summing those values. After computing these distances, we compare the player's distance to each ghost's distance. If the player's distance is less than every ghost's distance, then the player can escape, and we return true. Otherwise, if even one ghost has an equal or smaller distance, the player is caught, and we return false. There are a few edge cases to consider. If there are no ghosts, the player automatically escapes. If the target coincides with the origin, the player wins instantly since they are already at the target. Lastly, if any ghost is already at the target, escape is impossible because the ghost has effectively blocked the destination. The algorithm involves 2 main operations: calculating distances and performing comparisons. Calculating the Manhattan distance for each ghost is an O(1) operation, as it involves just a few arithmetic calculations. Comparing these distances to the player's distance involves iterating through the list of ghosts, making the overall time complexity O(n), where n is the number of ghosts. To optimize, we can terminate the function as soon as we find a ghost whose distance is less than or equal to the player's distance. This early exit prevents unnecessary calculations for remaining ghosts. Additionally, once the player's distance is known to be greater than a specific ghost's distance, further checks become redundant. The pseudocode outlines the logic clearly: compute the player's distance, iterate over the ghosts to calculate their distances, and compare. If any ghost's distance is less than or equal to the player's, the function immediately returns false. Otherwise, it returns true after all comparisons are complete. Let's walk through an example to see the algorithm in action. Suppose the target is at 2, 3, and there are 3 ghosts positioned at 1, 0, 4, 4, and 2, 5. First, we calculate the player's Manhattan distance to the target, which is abs 2 plus abs 3 equals 5. Next, we calculate the distances for each ghost. The first ghost, at 1, 0, has a distance of abs 1 to 2 plus abs 0 to 3 equals 4. The second ghost, at 4, 4, has a distance of abs 4 to 2 plus abs 4 to 3 equals 3. The third ghost, at 2, 5, has a distance of abs 2 to 2 plus abs 5 to 3 equals 2. Comparing these, we see that the player's distance of 5 is greater than the distance of the first ghost, which is 4. Therefore, the player cannot escape, and the function returns false. In terms of complexity, the algorithm runs in O(n) time due to the loop over the ghosts, and it uses O(1) space since no additional data structures are required. This implementation solves LeetCode problem number 789, escape the ghosts, by determining whether the player can reach the target position before any ghost. To do this, we use the Manhattan distance formula, which calculates the shortest path on a grid between 2 points. The first step is to compute the distance the player needs to travel to the target. Starting at the origin, 0, 0, this distance is simply the sum of the absolute values of the target's x and y coordinates. This is stored in the variable player_distance. Next, we iterate over each ghost's position. For each ghost, we calculate its Manhattan distance to the target using the formula abs, ghost, 0, target, 0, plus abs, ghost, 1, target, 1. This gives the shortest time the ghost would need to reach the target. If any ghost's distance to the target is less than or equal to the player's distance, it means the ghost can intercept or block the player, and the function immediately returns false. If no ghost can reach the target faster or at the same time as the player, the function concludes that the player can safely escape and returns true. This approach is efficient because it computes the distances in O(n) time, where n is the number of ghosts. It leverages the Manhattan distance formula, which is computationally simple, and avoids unnecessary calculations or complexities, ensuring optimal performance for this problem. This is the Java implementation of LeetCode problem number 789, escape the ghosts. It mirrors the Python logic, using Java's math library to calculate Manhattan distances. The method checks if any ghost can reach the target before or at the same time as the player. If so, the player cannot escape, and the method returns false. Otherwise, it returns true. The implementation uses standard Java arrays and follows typical Java conventions with type declarations and loops. Let's begin by analyzing the first example, which is a simple case. The player starts at the origin, 0, 0, and the target is located at 0, 1. To determine how long it will take the player to reach the target, we calculate the Manhattan distance, which is simply the sum of the absolute differences of their coordinates. In this case, the player's distance to the target is 1. Now, we check the ghosts one by one. The first ghost is at 1, 0. Its Manhattan distance to the target is calculated as 2. Since this is greater than the player's distance of 1, this ghost will not be able to block the player. Next, we evaluate the second ghost at 0, 3. Its distance to the target is also 2, which again is greater than the player's distance of 1. This means neither ghost can reach the target before or at the same time as the player. Therefore, in this case, the player can safely reach the target without any interference from the ghosts. Based on the previous analysis, the output for the first example is true because none of the ghosts can block the player. Now, let's consider the second example, where the player starts at 0, 0, and the target is at 0, 1 again. The player's distance to the target remains 1. Looking at the first ghost, which starts at 2, 0, we calculate its distance to the target. The Manhattan distance works out to be 3. Since this is greater than the player's distance, this ghost cannot block the player. At this point, the player still has a clear path to the target. Now, we check the second ghost in this example, which starts at 1, 1. Its Manhattan distance to the target is calculated as 1. Since this is equal to the player's distance, it means the ghost can reach the target at the same time as the player. When a ghost is able to reach the target at the same time or faster, it can effectively block the player from escaping. Therefore, in this situation, the player is unable to reach the target safely. The output for this example is false because the second ghost prevents the player from escaping. With this scenario covered, we can now move to an edge case to illustrate a different situation. In the edge case presented, the player starts at 0, 0, and the target is at 1, 1. Calculating the player's distance to the target, we find it is 2. Now, we examine the first ghost, which begins at -1, -1. Its Manhattan distance to the target is 4, which is greater than the player's distance of 2. This means the first ghost cannot interfere with the player's escape. Next, we look at the second ghost, which starts at -2, -2. Its distance to the target is calculated as 6. Once again, this is greater than the player's distance, so this ghost also cannot block the player. Since neither ghost can reach the target before or at the same time as the player, the output for this case is true. The player is able to escape successfully without any ghost interference. Here, we analyze the time complexity of the solution. The first step involves calculating the Manhattan distance from the player, starting at the origin, to the target. This operation is straightforward, requiring only two absolute value calculations and a single addition, making it an O1 operation. Next, for each ghost in the input list, we compute the Manhattan distance from that ghost's position to the target. Again, each calculation involves two absolute value operations and one addition, which is also O1. Since there are n ghosts, this computation must be repeated n times, leading to O(n) work for the ghost distance calculations. Finally, the algorithm compares the player's distance to the target with each ghost's distance. Each comparison is a constant time operation, O(1), and repeating this for n ghosts results in O(n) time spent on comparisons. Together, these steps give us a clear picture of how the operations scale with the number of ghosts. When we combine what we've discussed, the overall time complexity of the solution is O(n), where n is the number of ghosts. Now, looking at the space complexity, the memory usage is primarily determined by the input and a few auxiliary variables. The list of n ghosts, where each ghost is represented by a pair of coordinates, requires O(n) space. The target coordinates are a single pair, so they require only O(1) space. In addition, the algorithm uses a fixed number of variables, such as those for storing the player's distance and each ghost's distance during computations. These variables do not grow with the size of the input and therefore contribute O(1) to the space complexity. Since no additional data structures are used and the algorithm only processes the input directly, the overall space complexity is O(n), which is dominated by the input size. To better understand the efficiency of this approach, let's compare it with a potential brute force solution. A naive method could involve simulating the movement of the player in each ghost step by step, checking whether any ghost intercepts the player along the way. This would result in a much higher time complexity, potentially O(n*(d), where d is the Manhattan distance to the target. In contrast, the current solution eliminates the need for simulation entirely. By relying on direct distance calculations and comparisons, we reduce the time complexity to O(n). This improvement is significant, as the direct approach focuses only on the necessary computations. Furthermore, this O(n) complexity is optimal because we must check the distance for each ghost, meaning O(n) operations are unavoidable. The space usage is also minimized, as we only store the input and a few auxiliary variables, making this approach efficient both in time and space. Breaking down the performance further, let's consider the best, average, and worst cases for this algorithm. In the best case, if the first ghost in the list has a distance to the target that is less than or equal to the player's distance, the algorithm can immediately return false after a single check. This results in a time complexity of 1. On average, the algorithm will typically need to process about half of the ghosts before arriving at a conclusion, leading to an average case time complexity of n. In the worst case, none of the ghosts can reach the target faster than the player, meaning the algorithm must calculate distances for all n ghosts, which also results in n time complexity. Mathematically, these time complexities align with the fact that each Manhattan distance calculation is 1 and is repeated for n ghosts, making the total n. Similarly, the space complexity remains n, as it's dominated by the storage of the input. This analysis confirms that the solution is both time and space optimal for this problem. When tackling this problem, there are a few common mistakes to watch out for. First, it's crucial to use the Manhattan distance formula, which is calculated as the absolute difference in the x-coordinates plus the absolute difference in the y-coordinates. Some might mistakenly use Euclidean distance instead, but remember that both the player and the ghosts move in a grid-like manner, so Manhattan distance is the correct metric here. Another frequent error is not accounting for all the ghosts. The solution must ensure that no ghost reaches the target before or at the same time as the player. If even one ghost does, the player cannot escape, and the result should be false. Finally, a common pitfall involves off-by-one errors when comparing distances. If the player and a ghost reach the target at the exact same time, the player does not escape. Misunderstanding this condition leads to incorrect results, so careful handling of this edge case is essential. Now, let's address a couple of additional misconceptions. Overcomplicating the solution is a trap many fall into. Some try to simulate the movements of the player and ghost step by step or track intermediate positions, but this is unnecessary. The problem can be solved with simple distance comparisons, making simulation approaches inefficient. Another mistake is misinterpreting the target as dynamic or assuming the player can choose alternate routes. The target is fixed, and the player moves directly toward it, so overthinking this aspect adds needless complexity. Remember, simplifying your approach and sticking to the problem's constraints is key to an efficient and effective solution. For interview scenarios, there are a few critical insights to keep in mind. At its core, this problem simplifies to comparing the player's Manhattan distance to the target with the Manhattan distances of each ghost. Recognizing this early demonstrates clarity in problem solving, particularly for grid-based movement problems. Patterns to recognize include the frequent use of Manhattan distance in grid traversal problems, which can save valuable time during an interview. In terms of optimization, the solution runs in n, where n is the number of ghosts. If the number of ghosts becomes very large, interviewers might ask about scalability, so be prepared to discuss this. Edge cases are also important to consider, such as situations where a ghost starts at the target or the player starts at the target. These scenarios require explicit handling to ensure the solution is robust. Lastly, exploring related problems like grid-based BFS or shortest path problems can help reinforce these concepts. Examples include LeetCode 1162, 934, 1730, and 542, all of which involve grid traversal and distance calculations. Now let's examine alternative approaches to solving the problem. One option is brute force simulation, where you simulate each step for both the player and the ghosts, tracking their positions over time. While this approach is conceptually straightforward, it's highly inefficient, with a time complexity of d*n, where d is the average distance and n is the number of ghosts. A more optimal approach is to directly compute the Manhattan distance for the player and each ghost, then compare these distances to determine the result. This method has a time complexity of n, and leverages the problem's simplicity for efficient computation. Another useful technique is to use visualization or debugging tools. Plotting the grid or visualizing movements can help uncover edge cases or understand the dynamics better, though this method doesn't scale well for larger grids or numerous ghosts. Each of these approaches has its trade-offs, but recognizing the most efficient solution is key to solving the problem effectively. Great job completing this problem. In summary, we focused on using Manhattan distance to determine if we could outpace the ghosts. Key takeaways include the importance of distance calculations for grid problems and knowing when to use direct comparisons. Thanks for watching, and be sure to practice more problems to sharpen your skills. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!